In this lecture we're looking at topic 4. It's more on bonding, and it's something called covalent bonding. But I'd like to introduce that by just very briefly looking at metallic bonding. Now there are some notes on this in topic 5, page 4, and we'll have a look at it. I'll mention it again tomorrow, but I think it fits in a little bit better as a segue between ionic bonding and covalent bonding. When we look at covalent bonding, I want to tell you about what it is, and it is the sharing of electrons. I want to look at things we call bond pairs of electrons and lone pairs of electrons, and we find that when compounds bond, the electrons tend to pair up. I want to look at single, double and triple bonds, and at the very end a little bit about the nomenclature, the naming of covalent compounds. Recall that I mentioned that ionic compounds, we can understand their physical nature by knowing something about their bonding. The fact they're hard, brittle compounds with a high melting point relates directly to the fact that in a solid, the attraction between cations and anions is strong, so it's difficult to pull them apart, and that if we, by some means, give a blow to an ionic crystal, it will shatter, because we will displace what is attractive interactions between ions. We'll displace the ions such that then they'll turn into repulsive forces between cations and cations, anions and anions. So what are the characteristics of it? If I think about metals, you're familiar with the fact that you can beat metals into sheets, such as aluminium foil. Pretty much all metals can do that. This is a sheet of zinc metal. It's very pliable. It's malleable, to use the correct term. And it's also ductile, which means you can draw metals into wires, such as this. And you may have noticed today that the guys testing the electrical equipment in the School of Chemistry were around level 2. And until this morning, there was a much loved and favoured bit of equipment on the end of this, which I'm now not allowed to use. But you're familiar with the fact that metals can form wires. You're familiar with the fact that metals also conduct electricity. So how can we rationalise that in terms of the atomic structure of a metal? Well, this is how we think of the bonding within a metal. Let's start off by thinking that metals, on the left-hand side of the periodic table, form cations. And imagine a situation where I have a number of metal cations. But instead of balancing these charges with negatively charged anions, as happens when sodium and chlorine combine to give sodium chloride, in a metal on its own, the electrons remain associated fairly closely with the cations, but not associated with an individual cation. So the idea is there's a whole group of cations with a sort of a glue of electrons that holds them together between them. Now the consequence of this is twofold. If, for example, I now put a shearing force on one part of this metal and push those cations to the right, the electrons will take up the slack. They'll rearrange themselves so that they will always provide some sort of attraction between the cations and the negatively charged electrons and those and other cations. So you can manipulate the crystal structure of a metal in order to get the atoms lined up in a sheet in 2 dimensions or in a wire in 1 dimension, if you think of it that way. So unlike ionic materials, we can stretch, we can beat into sheets metals. The other characteristic of metals is that they conduct electricity. And you can imagine a situation where if we put a battery, a potential difference, across a metal, It can conduct now because I've got electrons which are very, very small particles, and they can move in between the cation lattice. So I can feed electrons in at one end, and they will flow through the metal, and I can get electrons out of the other end. And hence, metals conduct electricity when they are solid, unlike an ionic compound where we have fixed positions for the cations and anions. Both cations and anions have considerable size and so can't move relative to one another. So that's a little bit of our model of metallic bonding. What about this stuff, covalent bonding? There's a little bit of a problem. Let me start off by getting you to imagine what happens when I take a magnesium atom. I can remove an electron, and maybe I'll just draw the outer electron shell for magnesium. These core electron shells filled with electrons. I know that magnesium, if you like, needs to lose 2 electrons in order to gain a situation where it has a completed electron shell. Removing 1 electron, well, I have to put in a little bit of energy to give a magnesium plus ion. But that still has 1 electron in its outer shell, and I need to remove that in order to strip the magnesium back to a noble gas electron configuration, that of neon. But the difficulty is that while removing an electron from a neutral atom is hard enough, removing an electron from something that's already positively charged is getting really difficult. And if I take this to the extreme, if I imagine carbon, think of the electron configuration. There are 4 electrons associated with the carbon atom. If I were to strip them off so that I end up with a noble gas configuration, just the inner shell filled with electrons, I would have to remove a total of 4 electrons and this might occur in sequential steps. And while I might be able to remove 1 electron from a neutral carbon atom easily enough, by the time I get up here, removing an electron from something that's already triply positively charged, that requires huge amounts of energy. And any stabilization that I get from forming an ionic compound is not nearly enough to compensate for the energy I have to put in to form this 4+ cation. Similarly, what I could do is say, how about we add electrons, firstly to get C-, then C2-, then C3-, and finally C4-. That also has a completed electron shell, but the same problem occurs. I might be able to add 1 electron to a neutral atom without too much problem. Adding something that's negative to an anion that's already negative becomes much more difficult, and something that's really problematic is adding an electron to a 2- anion, and once again the energy needed to form a C4- anion is just huge, and it's very much greater than any energy you would get out from forming an ionic compound when carbon was an anion. So it doesn't work. There's got to be another form of bonding. The other reason that we suspect there's another form of bonding is we know that some elements like hydrogen, oxygen, nitrogen, chlorine, fluorine, bromine form diatomic molecules in their natural stable state. So we can ask the question, how is it that two hydrogen atoms are bonded together? Is one an H plus and another an H minus, or what happens? And the answer again comes down to electron configuration and the need, the desire to be anthropomorphic about it for a completed electron shell. Single hydrogen atoms have just one electron in that first electron shell. To fill that first electron shell, I need two electrons. What I could do is, rather than transfer electrons from one to another, I could share electrons between the two atoms. And when I share a pair of electrons, I have what we call a covalent bond. One shorthand way of writing that is just with a dash, where the dash indicates a pair of electrons. And we find that quite commonly in chemistry, electrons tend to pair up, and we can illustrate that here. And now both hydrogen atoms experience what effectively is a completed electron shell for hydrogen. So let's move on and look at something like carbon. If I write out just the outer electron shell of carbon, carbon's row 2, the core electrons are in the first shell, and that's filled. The second shell has 4 electrons in it. Carbon is 4 atoms from the left of the periodic table. I predict, another 4 electrons if I'm going to form a stable compound of carbon. And one way I can do this is to react carbon in a way that it will combine with 4 hydrogen atoms. Each hydrogen atom provides 1 electron. I have sharing of electrons between hydrogen and carbon. And from the hydrogen point of view, the hydrogen now experiences an electron pair, which is what it wants to complete its electron shell, the first shell. Carbon now experiences a total of 8 electrons, which is what I want to complete the second electron shell. So our bonding model for carbon, in this case, is one of sharing electrons between 2 atoms in a way that gives carbon a total of 8 electrons. And in this case, it is 4 bonds give us a total of 8 electrons. I would predict then that the stable compound between carbon and hydrogen has the formula CH4. It's not going to be CH, it's not going to be CH5, it's not going to be CH3, because that wouldn't satisfy 8 electrons associated with the carbon. So the only way I can end up with completed electron shells is with this particular ratio. Now let's look at another compound that you're familiar with, water, H2O. And if I think of the electron configuration of water, again I'm going to draw just the outer electron shell. Sometimes we call this the valence shell. Say more about that later. Oxygen, group 16, has 6 electrons in its outer shell. The core electrons are not involved in bonding, so I will leave them out of the diagram for a moment. And if now we react oxygen with 2 hydrogens, and we're starting to look like Prince Charles here, I think. If we have a situation where we have 2 hydrogens reacting with a central oxygen atom, that will give us a molecule in which each hydrogen provides 1 electron, oxygen provides 6 electrons. I pair up the electrons such that the hydrogen experiences an electron pair, and that is what it wants for a completed electron shell, and the oxygen now has 8 electrons associated with it. How can I draw this? I might draw it like that, but also notice for my electron diagram that I've got pairs of electrons that are not associated with bonding and other pairs of electrons that are associated with bonding. Perhaps not surprisingly, a pair of electrons associated with bonding are called bonding pairs. And then the electrons that are not associated with bonding, and in some cases we add those in because they're important to the chemistry, we call those non-bonding or lone pairs. Non-bonding pairs or lone pairs of electrons. In all cases, in our shorthand diagram, we're actually focusing on just the electrons in the outer shells of all the atoms. We ignore the ones in the inner shells, the core electrons, because they play no part in the bonding. One more example in this suite of compounds is ammonia. NH3. And if we think what we're doing in the periodic table, we're looking at basically carbon, nitrogen, oxygen. We've done carbon and oxygen. Looking at nitrogen, well, it has one more electron than carbon, one less electron than oxygen. If I draw the outer shell electron configuration, the valence shell electron configuration, I find that there are 5 electrons there. If I pair this up with another 3 electrons, one each from 3 hydrogens, then I get a situation where nitrogen has the expected 8 electrons associated with it. If I was to draw this in terms of our shorthand diagram, I might see that there are 3 bond pairs of electrons and 1 lone pair of electrons in nitrogen. Okay, so we have lone pairs and bond pairs. We can use this sort of model to predict the formula of compounds. When nitrogen and oxygen combine, I would expect the formula to be H2O and nothing else. We'll find that if we have a charged species, then things may be a little bit different. But oxygen, we find, will end up always with 2 bonds. Nitrogen, in neutral molecules, will end up with 3 bonds, and carbon with 4 bonds. There's a pattern there. And one concept I'd like to introduce is one of valence. Now, if you look at the periodic table, we say that everything in group 1 has a valence of 1, group 2 valence of 2, group 13 valence of 3, valence of 4, valence of 3, valence of 2, and group 17 elements have a valence of 1. So looking across the periodic table of the green and orange groups here, you count 1, 2, 3, 4, 3, 2, 1. No valence associated with the inert gases. Valence is to do with bonding. Inert gases don't do any bonding, so there's no valence associated with them. Valence is a concept that says that if that element forms an ion, the valence gives the magnitude of the charge on the ion. It doesn't tell you whether it's positive or negative. You have to deduce that from its position in the periodic table. But if that element forms a covalent compound, the valence tells you the number of bonds in that covalent compound. So, something like oxygen, valence of 2. When it forms an ionic compound, it will form a 2- ion. when it forms a covalent compound, such as water, it will have two bonds. Nitrogen, if it formed an ion, it would be a 3- ion. If it formed a covalent compound, you'd expect it to have 3 bonds. This side of the periodic table, valence of 2 associated with the group 2 elements. Well, they don't tend to form covalent compounds, but we can still use the concept of valence to say, okay, the magnitude of the charge on the ion is going to be 2. From the position in the periodic table, we know it's 2 plus. Look, as a little bit of a diversion, I've got some molecular models indicating carbon, CH4. I've portrayed it as if it's a flat molecule. It's not a flat molecule, an artifact of a two-dimensional blackboard. It's actually a tetrahedral shape. NH3 also is not a flat molecule. It's not even T-shaped, as I've suggested, but it's a pyramid, such as that. And water has actually is an angular molecule, or a bent molecule, or some would say a V-shaped molecule, like that. And I want to just digress a moment to suggest to you how we get those shapes. Why is it that water is this angular molecule and that the hydrogens are not at 180 degrees to one another? And I'm going to try and illustrate this with balloons. This might not work. Halfway there. I was practicing this at Leichhardt Market Town Shopping Centre, making little kangaroos over the weekend. It wasn't very successful there either. Now, okay, when electrons form bonds, we can imagine that we've got, in this case, 4 areas. In fact, all these 3 cases, we've got 4 areas of electrons. And depending on which molecule, they are a combination of bond pairs and lone pairs. Now, electrons are negatively charged, so they will try and get it as far away from each other as possible. They will repel each other. So if you imagine I cut my fingernails last night especially. If you imagine we have 4 areas, we've arrived and this has been successful. If we this is I perhaps should not have, maybe I thought just as a backup I will bring another couple of balloons if those didn't work. And imagine we've got 2 areas of electrons. The best way 2 areas of electrons can get away from each other is if we've got a linear molecule. And that's going to be more stable than a molecule with a 90-degree bond angle. If we have 4 areas of electrons, then I don't get something that's flat. I get something, if you'll just make a little bit of allowance for the bends and so on. I get something that is 3-dimensional. And what I want to show you is it is approximately a tetrahedron. And I don't know whether that approximates it or that approximates it closer, but we've approximately got a tetrahedron. And that indicates that if all those bonds, if all those electron areas were bond pairs, then we'll have a tetrahedral arrangement as we have in something like CH4. If, on the other hand, we happen to have, say, 1 lone pair and 3 bond pairs, when we view a molecule, we can only see the position of the atoms. The electrons are too small to see. So it's kind of like taking a tetrahedron and then imagining we can't see one part of it, which is the lone pair of electrons. What we're left with is this pyramidal shape. And then take this one stage further. If we have a water molecule, and imagine, for example, if these are electron pairs, imagine that we can't see 2 of these electron pairs. and the other two are bond pairs of electrons. What we will see is something that was based primarily on a tetrahedron, but we can't see kind of a couple of the arms of the tetrahedron. And what we observe, if I line up my water molecule with my methane, what we observe is an angular molecule that has two bond pairs. And we can't actually visualize the position of the lone pairs, but we know they're there in the other axes of the tetrahedron. So molecules have shape, and in particular in a biological context, this can be really, really important. Okay, so that's a little bit about lone pairs, bond pairs in molecules such as this. I want to look at another couple of molecules, and to start off with, I want to combine carbon with oxygen and look at what happens with carbon dioxide. Perhaps I should, before doing that actually, look at oxygen itself. I told you before that of all the elements, there are a few that exist as diatomic molecules. Hydrogen, top of the board, oxygen, nitrogen, fluorine, chlorine, bromine, iodine. And they always exist as diatomic molecules. But what about something like oxygen? What's our bonding model for O2? I've told you that oxygen has a valence of 2 and forms 2 bonds. Let's see what happens if we do the electron dot diagram. I'm going to sort of colour code the oxygens. I'm going to sort of arrange the electrons in the atom in a way which actually seconds guesses what my answer is going to be. If I share electrons like that, I end up with an oxygen-oxygen single bond, and the left-hand oxygen will have 2, 4, 6, 7 electrons associated with it. Heading in the right direction, but not good enough. Similarly, the right-hand oxygen has 7 electrons associated with it. What I could do is share 2 pairs of electrons, 2 electrons from each oxygen, and if I was to redraw this, I might redraw it like this, where the left-hand oxygen has 2, 4, 6, 8 electrons associated with it, so that's going to be the stable form. Right-hand oxygen has 8 electrons associated with it. I have not 1 electron pair, but 2 electron pairs between the 2 oxygen atoms, and we call that a double bond. So, oxygen has a valence of 2. In an O2 molecule, each oxygen atom has a double bond rather than, say, 2 single bonds as it has in an H2O molecule. Oxygen also has 2 lone pairs, just as it has in a water molecule. So the lone pairs don't change, but the bonding arrangement does change. And valence tells us just the total number of bonds. It doesn't tell us whether it's single bonds or double bonds. Here I've got 1 double bond, 2 single bonds. In both cases I end up with 8 electrons associated with the oxygen. Well, perhaps you can imagine what's going to happen with carbon dioxide. You're probably familiar with the formula. If I look at the electron dot diagram of carbon, and if I imagine oxygen with its 6 electrons nearby, I could imagine a situation where sharing 2 electrons on each of the oxygen atoms with the 4 electrons of the carbon atom will give me a situation where the oxygens have 2, 4, 6, 8 electrons associated with it, 2, 4, 6, 8. So the oxygen has now got the 8 electrons, the closed shell, the noble gas electron configuration, which makes it stable, and carbon has 2, 4, 6, 8 electrons associated with it. And I would predict the structure of carbon dioxide to have carbon with 2 double bonds and each oxygen with 1 double bond to give us a stable molecule. Consequently, the formula of compounds is not random, whether they're ionic or covalent. It all depends on the electron configuration. Let me do another couple of examples of this before looking at a bit of naming. If I have, say, nitrogen gas, a diatomic molecule, what is the electron configuration? Well, you might be able to sort of guess this by the fact that I've already mentioned that nitrogen has a valence of 3. We've seen in ammonia, nitrogen forms 3 bonds. Imagine a situation. How do we calculate that? How do we rationalize that? I write down the electron configuration of the outer electron shell of the nitrogen. I then pair up the electrons in a way that gives me a total of 2, 4, 6, 8 electrons on each nitrogen atom, and as a consequence of that, I predict this molecule to be stable. Drawing our shorthand, I have a triple bond between the 2 nitrogen atoms. I want to do 2 more examples, both of carbon compounds. We've seen a carbon compound where we have 4 single bonds, it's in CH4. I've seen a carbon compound where there are 2 double bonds. I want to do the other 2 scenarios of bonding that will give us a total of 4 bonds on carbon in the stable situation, whatever it combines with. And the first arrangement, I'm going to do this, if you like, in the other direction. I'm going to give you the final answer. This molecule is called ethylene, and I'm going to prove to you that it's a stable bonding arrangement. C2H4. Each carbon has 4 bonds associated with it. Each hydrogen has 1 bond associated with it. If I look at the electron dot diagrams, start with hydrogen. I might have analysed this compound and found the formula to have twice as many hydrogens as carbons by trial and error, and there really is no substitute for just trying out with pen and paper a structure, seeing whether it gives a stable arrangement. What I could do here is have, say, a hydrogen there and a hydrogen there. I can pair up those bonds and on the right hand carbon, as I've drawn it, put 2 more hydrogens there, and you can see that I've now got a situation where each carbon has 8 electrons associated with it, each hydrogen has 2 electrons associated with it. I would predict that to be a stable bonding arrangement, and indeed it is. No lone pairs in this case, only bond pairs. And as a final one of these examples, if you think about the possibilities of bonding in carbon, I can have 4 single bonds. I could have 1 double bond and 2 single bonds. It's in the carbon here. I could have 2 double bonds. 2 and 2. Or I could have one single bond and one triple bond. And that is what we have in the molecule of acetylene. Has that structure. I don't know whether anyone's done any oxyacetylene welding. What you'll find is that all gases come in cylinders that are colour-coded. So if you know any plumbers or see a plumbing ute on the back of which there's some welding equipment, you'll see that there is a tall cylinder which is black with a grey top, and that's oxygen, and you'll see a small squat cylinder which is a sort of maroon colour, and that actually contains the acetylene for oxyacetylene welding. Acetylene itself is actually a very explosive gas, and if you pressurise it, it tends to explode. So what happens in those cylinders? If you ever come across one and you shake it, you'll hear a liquid inside it. It's actually not pressurised acetylene, but it's acetylene dissolved in a solvent. And when you open the tap at the top of the cylinder, the gas in the headspace above the solvent is released, and the gas that's dissolved in the solvent then comes out of solution, rather like, you know, bubbles out of Coca-Cola when you take off the top. So acetylene, a very explosive gas. Why is it that this is the formula for it? If I look at the bonding model, carbon, 4 electrons in its outer shell, hydrogen, 1 electron in its outer shell, and I can see hydrogen can only ever form one bond, a valence of 1. Carbon has a valence of 4. It always forms 4 bonds. But the bonding arrangement doesn't mean to say it's always 4 single bonds. It could be 4 single bonds, it could be 1 single and 1 triple, as long as the sum adds up to 4. And in all compounds, whether they be covalent or ionic, we can rationalise the ones that are going to be stable based on an electron configuration that mimics a noble gas or an inert gas. Okay, now I've actually given a couple of examples that have non-systematic names. Ethylene, acetylene, and these are the names that, in these cases, these gases are known by. I'd like to just mention a few words about the naming or nomenclature of compounds in general that are covalent. All the examples actually, even water, ammonia, they are so common that they are given common names, not systematic names. We actually name covalent compounds really in exactly the same way as naming ionic compounds. There are 2 parts to the name. The first part is generally associated with the atom of the lower group number of the atoms that are bonded. It's the atom on the left if you look at their relative positions in the periodic table. And let me give you a molecule which we'll use as an example, SF6. Say, if I look at the position of sulfur and fluorine in the periodic table, sulfur has a lower group number, it's on the left. That is named first, it's named as the element. So no change there. The element is bonded to, it's named as if it was an anion, as if it were an anion. And we have to indicate how many there are of them. So in this case, sulfur, hexa, fluoride would be a name for this compound, SF6. If I looked at another example, let's say N2O3. we find that the picture of bonding that I've given you actually works for the vast majority of compounds. Valence, the concept of valence, works for the majority of compounds, in particular row 2 compounds, covalent compounds. As we get to compounds formed from atoms lower down in the periodic table than the second row, then there's usually more options. And there's usually more options because what we're dealing with are electron shells which are bigger, further out from the nucleus, and actually can accommodate more electrons. So some compounds, like sulfur, can have a range of bonding models. And while sulfur does have compounds in which there are 2 bonds, H2S, hydrogen sulfide, the direct analogue of H2O, there are also compounds of sulfur that have 4 bonds, SF4, sulfur tetrafluoride, and SF6, the one here, sulfur hexafluoride. Nitrogen also always forms 3 bonds in its neutral state, but that can actually give you a range of different compounds. I've shown you ammonia. There is another compound that has this formula. How do we name it? Combination of nitrogen and oxygen. If I look at the relative positions of those atoms on the periodic table, nitrogen's on the left-hand side, so we name that first as if it's the element, nitrogen. I name the oxygen as if it were an anion. But because there are a range of compounds between nitrogen and oxygen, I need to specify the number of atoms of each sort that are present in this molecule. And in terms of the nitrogen, there's 2 of them. So I use the multiplier di. In terms of the oxygen, there are 3 of them. So I use tri. Dinitrogen trioxide is the correct name for this compound. If there's only one of those atoms, such as the case in sulfur, we don't tend to put mono. We assume it's a single atom unless otherwise stated. So rather than monosulfur hexafluoride, it's just sulfur hexafluoride. 2 or more, we have to use di, tri, tetra, penta, hexa, and so on. Now, one final aspect of this is that there are some ions that we call polyatomic ions, and they're a combination of covalent bonding and charges. And I think the best thing I can do is point you to Table 3, page 8 of the book for examples of polyatomic ions. I want to wait for the camera to come up. I want to also mention that in this case you have exactly the same procedure for determining the formula of compounds that involve polyatomic ions. We'll walk through a few of those ions and then I'll do a couple of examples of naming. Here they come. So, nitrate, nitrite, and so on. What we find is that in this case, we have a collection of atoms that are held together by covalent bonds. And overall, the number of electrons are such that we have a total charge on that ion. The vast majority of polyatomic ions are anions, and there's a set of examples here. There are just 1 or 2 cations that are polyatomic ions, and one of those is the ammonium ion, which has the formula NH4+. There's no easy way of remembering these. There's no easy way of remembering these, but there's something that we'll actually do in first year chemistry, and I don't want to sort of dwell on them now. What I do want to do is just pick a couple of examples to show how we can determine the formula of these more complicated compounds. And if we say, look at a combination of potassium and sulfate, I look up my table, I find that there's an ion called sulfate which has the formula SO42-. It will form an ionic compound in combination with potassium, which from its position in the periodic table I know is K+. So I'm using this crossover method. There's one there. That one now refers to all of the sulfate ion. A ratio of 2 potassium cations to 1 sulfate anion will give us our expected formula for potassium sulfate. Let me do one more example. NH4+ is a polyatomic ion. It's called the ammonium ion, and that will combine with an anion in exactly the same way that you expect for an ionic compound. Let's combine it with another polyatomic ion, carbonate. If I use the crossover method, I have 2 lots of that, 1 lot of the anion. And I keep all those atoms together by use of brackets. 2 lots of the ammonium ion, 1 lot of the carbonate ion to give me ammonium carbonate, formula of ammonium carbonate. Okay, so summarising that, if we don't form ionic compounds, we can form covalent compounds. Covalent compounds tend to be formed by elements bonding together where the elements are fairly close in the periodic table. Ionic compounds are when we combine elements from the far edges of the periodic table. In covalent compounds, we share electrons in a way that each atom ends up with a completed electron shell. We can predict how many bonds a covalent compound will have for each of the atoms it contains by looking at the valence of the atoms. And valence is something that, if we go from the left to the right of the periodic table, missing out the middle bit, goes 1, 2, 3, 4 by group 14, 3, 2, 1 by group 17. Indicates the magnitude of the charge if that element forms an ion. It indicates the expected number of bonds in the uncharged state if that element forms a covalent compound. The worst bit of it all is that we can get combinations of covalent and ionic where we have what we call polyatomic ions. These are clusters of covalently bonded atoms that have an overall charge. We'll go into these more in Chemistry 1, but just be aware of them now. They follow the same rules in terms of determining the formula of an ionic compound associated with polyatomic ions.